In this video, we're going to learn one more trick in order for us to get a usable microscopic model for entropy. And so we saw that, if we had n number of molecules in a system, the number of different ways of arranging those molecules is incomprehensibly large. But what we could do is we could calculate the entropy of the system, which is just the natural logarithm of that number. We calculate the entropy, and that gives us a more manageable way of discussing and handling the number of different ways we could organize molecules in our system. Okay? All right, and so this is the definition, this is the definition of entropy at the microscopic scale. And so what we're going to do is we're going to take the multiplicity formula we derived for an ideal gas, and we're just going to plug it in to this definition for entropy. Okay? All right, and so from the previous videos, 2 videos ago, we developed this equation to describe the omega of an ideal gas. Vn U3n of a monatomic ideal gas. And so we're going to plug this into our entropy equation. Okay? So when we plug that in, we get this. Essentially, I'm just going to take a shortcut and copy and paste this. All right? And I mentioned, we took the natural log of omega because it allows us to handle these numbers more easily. And specifically, by plugging in omega into the natural log, we could use our log rules in order to manipulate the formula. So what I'm going to do is I'm going to rearrange the formula a little bit and split up the terms that have a factorial h to the 3. Oh wait, no. So this is squared, but this is to the 3 halves. There's v here. So internal energy is in here, in the 3 halves. Volume's out here by itself. All right, so I isolated these terms, and what I'm going to put over here are all the terms that had like a factorial in them. Divided by 2 factorial. Okay? Right, so essentially I moved this term and this term. Using log rules, we're able to say, since they're being divided out, we're able to say that's equivalent to just being the minus natural log of that. Okay? All right. In any case, the n factorial, we're taking the natural log of it to make it a smaller number. But the fact that it's a factorial it's still a really large number, right? And so it's still, kind of, and if we're dealing with 1 mole of gas molecules, that means we have Avogadro's number of gas molecules, 10 to the 23. And so that means that the natural log of 10 to the 23 is still really big. All right, but what we could do to at least make this number a little bit more manageable is we can make an approximation. Okay? And so to calculate, I guess, the natural log of n factorial and natural log of 3n divided by 2 factorial, what we could do is we could use something called Stirlings Approximation. won't prove Stirling's approximation for you. It's kind of complicated. But essentially all Stirling's approximation is that it says that the natural log of n factorial is basically equal to n times the natural log of n minus n. Alright, that's just what the identity is. Okay? And so with that identity in hand, we could go back to equation 1 and we could simplify equation 1 down to this form. S is equal to n kb. So we pulled out the n entirely. And then inside the bracket, we have v over n 4 pi m u 3n h squared to 3 halves. Okay? Right, so that all this stuff is in the natural log. And then we have just a 5 halves out here. Okay? Right? And so for an ideal gas, for a monatomic ideal gas, this is what our entropy equation simplifies down to.